also w divided by log to the epsilon? I guess so. Depends how you count. Let me think for a second how these edge indices should be stored. I think I'd like to store the edge indices. I don't want to store the absent down pointers. Okay. The way that I built this tree, this compressed trie, I was always adding things to the right. So it's like, okay, I'm storing here. Here's the first child. Here's the next child. Here's the next child. Here's the next child. I just keep appending on. It's like an array that you can grow to the right, which you should know how to do in constant time. Even a linked list is probably fine. I don't want to store, if there are a bunch of values here that are just null pointers, I don't want to store those items in the array. Okay, so in fact, the maximum number of children of a node is n. I mean, at the worst case, you have branching everywhere. So this is only log n bits. To store the index in that array. So it's an extra level of compression, I guess I didn't mention. Don't store null pointers, just skip them. And that's easy to do because always just appending. And in the end, what do I need to do here? Step 7 is in-order traversal of the compressed trie. And I output all the leaves I get in order. And the point is, we computed the compressed trie, which has the rough, correct topological structure. Then we fixed the order within each node. Now we have the correctly sorted compressed trie. And so you just do an in-order traversal, output the leaves you get in order. Boom, we've sorted all the items. Okay, a little crazy. So if all we need to do in the end is in-order traversal, then it's fine. We don't need to store the null pointers. So we don't need to be able to search in this trie. So this is enough. Clear? OK, the remaining question is how expensive is this recursion? So I computed the number of bits is basically w divided by log to the epsilon n plus order log n. The order log n won't hurt us. Now we started with integers of size w. Total size here was w. Now we have integers that their size is w divided by log to the epsilon n. So we've made progress. Cool. How much progress? Over here, maybe. So after, let's say, 1 over epsilon plus 1 recursions, we will have reached B will have decreased, excuse me, to order log n, I guess like 1 over epsilon log n plus w over log to the 1 plus epsilon n. Okay. Right? If we take w and every time we divide by log to the epsilon n, then after 1 over epsilon times, we have divided by log n. Get rid of the epsilon. Do it one more time. We get w divided by log to the 1 plus epsilon n. Okay, and at this point, we're in good shape. Okay, if we get the size of our integers to be only w divided by log to the 1 plus epsilon n, then we can use pack sorting. Because pack sorting, conveniently, it's a black box at the moment, says, well, as long as w divided by b is a little bigger than log n, so here we've made it quite a bit bigger than log n, I mean log to the 1 plus epsilon n, bigger, then we can use pack sorting. So reach base case, and then use packed sorting. Okay, the only thing is there's this log n. Now, epsilon is a constant here, so 1 over epsilon is constant. So this is just order log n. Order log n doesn't hurt you. I mean, if this happened to dominate this, then you're saying your values are order log n bits long, and so you use radix sort. Okay, so that's not going to dominate. In fact, you can prove in this case it's not going to dominate. W is at least log to the 2 plus epsilon. So you take W divided by log to 1 plus epsilon, that's still at least log n. Okay, so this will always dominate. Okay, so we did all this work, and all we did was reduce our word size by a log to the epsilon factor. But that's enough, because after we do that, 1 over epsilon plus 1 times, we're small enough, the words are small enough, or the items we're sorting are small enough that we can use pack sorting. And boom, we're done. Okay, that is the beauty of signature sort. Any questions about that? Definitely not easy. But it works. The crazy idea is, well, decompose into these digits. I mean, we decompose into log to the epsilon digits because that would be enough. If we could get things down to a single digit, life would be easy. Which I guess is kind of like Venom de Boas, right? I mean, or it's like our lower bounds from last time. I don't know. Only one, if we could make it so only one digit mattered, then we could afford to do it because each digit is quite a bit smaller. I mean, it's smaller by a factor of log to the epsilon n. So we did that splitting, and then there was this observation that, well, most digit values aren't used. So if we hash, then things got a lot smaller. Then we can afford to pack sort, except that hash didn't preserve the order. How didn't it preserve the order? Well, when you look at the compressed trie, you see how it got messed up. Each node got messed up individually, but overall the structure of the trie was correct. So we did all this work to get the structure of the trie, then we had to fix the node order, but that's really just sorting a single digit. And yeah, we have to do it for all nodes, but you add them up, it's still only n items that we need to sort. So I wrote that B went down. N stays the same. The number of things we have to sort stays the same, which is fine. I'm not trying to reduce n, I'm just trying to reduce the size of our items to be a little bit smaller than W, so then we can use pack sorting. Okay, I think I've gone over this algorithm enough times. The next step is pack sorting. Now that if we have integers that are much smaller than our word, how do we sort in linear time? And this is going to be essentially a fancy merge sort. It's done in the same paper. Before we said omega, I'm going to essentially make omega a little bit bigger than 2. So I want to assume that W is at least twice B plus 1 log n log log n. That's just to make this convenient, but of course it doesn't really matter what the constants are. This will make everything fit in one word, though, instead of a constant number of words. OK, step 0 of this algorithm is the packing part. We can fit more than one element into each word, so put them in. Okay, now we have linear time overall. This is easy to do. Just you have some word already. Take those items, shift them left or in the next item. Shift them left or in the next item. Shift them left or in the next item. Okay, linear time. So in the end, what it's going to look like. Oh, I also want to leave a 0 bit in between each of them. So we're going to have B, this is going to be x1 here, x2, xn. Each of these is b bits long, and then we have one more bit. And in fact, the way we set things up, this is only half the word. So there's another half over here, which is going to be all 0 for now. So we have one word contains, or sorry, this is not n items. This is going to be log n, log n. Can't fit them all in one word. That would make life really easy. But you can fit log n items in the first word, then the next word is the next log n items, and so on. Okay, linear time to do that. Next step, this is an algorithm. It's not really a step, I should say. These are things that we're able to do, and we're going to combine them in different ways. So the next thing to observe, this is a sort of bottom-up perspective. So first thing we can do is pack things into a word. Next thing we can do is merge two sorted words. Let's say they each have k items, and k is at most log n, log n. And I want to merge them into one sorted word. With 2k elements. So I have two of these things, and I'll merge them in sorted order. Okay, when I did this packing, nothing's sorted, but don't worry about that at the moment. Just if I had two of these words, and suppose they were already sorted, then I want to merge them and make them still sorted. Okay, I want x1 to be less than x2, and so on. How much time? It'd be cool if you could do this in constant time on a transdichotomous RAM. You could do anything on a constant number of words in constant time. We're not going to achieve constant time, but we don't need to. We're going to do order log k time. This is the hardest step of pack sorting, and I'm not going to tell you how to do it until later. I will tell you, don't worry, but this is going to require bitonic sorting. So I have to delay it a little bit. Suppose you had that for now. Let me tell you how the rest is easy. So many black boxes, but they're all filled in this lecture. Okay. Next thing you might ask is, well, how do I get a sorted word? I see how to get a single word that has log n items, but how would I sort those items? Use merge sort. Here's a merger. You have a way to merge two sorted lists, so use merge sort. That will give you a way to sort the whole thing. So I'm going to merge sort k equals log n items. Into one sorted word. So I start out with a word that's unsorted. I do merge sort, and I sort them. Okay, so this is not the whole sorting problem, but it's the one word sorting problem. So how long does this take? Well, it's the usual merge sort recurrence, but then it's plus how long it takes me to split the word. Well, splitting a word is easy. You just mask out the low end or the high end, and then maybe shift over. So in constant time, I can get the left half and the right half of the array, which is the word. Then the hard part is merging them, and merging them is 1, and that takes log k. So this is step 1. That's our merger. And so what does this solve to? Well, probably easiest to draw the recursion tree. So at the root, we pay log k. Then we have 2 times log, I guess, k over 2. Log k over 2. Okay, so at this level, we're paying log k. At this level, we're paying 2 log k minus 1, I guess. Okay, I'm just going to call this maybe, well, yeah, I do need to do that. At the bottom, I mean, everything's constant size, so you pay constant. How many leaves are there at the bottom level? K of them. Okay, so at the root, we're paying log k. At the leaves, we're paying k. This is roughly geometric. There's this minus 1, but it's geometric enough that when you add up all these levels is dominated by k. And so this ends up being order k time. Okay, the -1 here turns out not to matter much. Cool. So this is linear time sorting on log n, log n items. Everything that fits in a word. Cool. But we're not done yet. We need another level. The rest is pretty easy. It's just scaling up. Okay, let's see. At this point, we're going to assume that all of our words are completely full. So this merging and stuff was in order to fill up words and to make those words sorted. But once we've done that for each cluster of log n, log n items, now we can assume each word is sorted and completely full. It has exactly k elements in it. So each of these r-sorted words has k elements. Okay, so now the issue is things don't fit in a word. And so now suppose they fit in r-sorted words. So suppose we've already made a sorted list of of r times k items, which fit in r words, each with k items in it. Then I want to take two of these lists and merge them together and get one sorted list of sorted words. So it's two rk items that are distributed into two r words, each of size k. How do I do that merge? In linear time, and I only need to do it in r log k time. Only. Yeah, question?
You're assuming k is the number of elements per word now.
K is this from now on, and they're exactly k elements per word. Which is, I mean, we've already filled up the words, so at this point we can assume that.
Okay, but it's exactly equal, not less than or equal.
Right.
Yeah,
Yeah, over here it's less than or equal to. I know it's a little confusing. I use k for a different, call this k prime. Okay, and at this point we filled up to this value of k. And now everything has exactly log n items. Thanks. Okay, let's see. I mean, regular sorting out, regular merging algorithm would take r times k time because there are r times k items. But we have this merger over here, which will merge two words in log k time. So that's why it's going to be r log k. What's the picture? Well, let me draw it. We have a list of words. A list of words. How do we merge? Well, we take the first two words, merge them. When we merge them, and we know how to do this in log k time, by step 1. When we merge them, we get two words. They just are now sorted. Okay? So we've got these two guys sorted, and then there's the rest. I'd like to say output these and repeat, but that wouldn't be quite correct because, well, these guys I can output. Because I've got k items here, k items here. These are the k smallest among all of them. Those must be the overall smallest k items because I compared k with k. These higher k items, I don't know. They could, they might be good or bad. So I have to put this high part back into one of these lists. We have to think a little bit about which list to put it into. It turns out if you look at the max item, say where did this come from, list 1 or list 2, you put it into that list. Let's say this came from list 2. Then you put it back into list 2 and then repeat. Okay, so in log k time here, we have output k items. And so we end up with an r log k running time overall. Okay, so it's like the regular merge algorithm, except we use step 1 to merge words. And then there's a little bit of work. But this was like the old merging algorithm, right? You take the min and you put the max back in. Okay, except now the max is a whole word. Okay, that's how we merge. Now why do we do a merger? Because the next thing we do is merge sort. And this is the overall algorithm. It's one merge sort. We're going to use this as the merger, and we're going to use this as the base case. So it's actually two recursive levels of merge sort. Merge sort is recursive within step 4 for a while until we get down to the level of a single word. Then we use this thing to deal with things in a single word. Okay? So we end up with T of n is 2 times T of n over 2 plus n over k log k. And a base case of T of k is order k. Okay. Why is it all this? Okay, this thing is r. Okay. So we have r log k to do a merge. R here is n over k. Why is it n over k? Because n is the total number of items. We had r times k items, so n equals rk. So r equals n over k. Okay, that's that. So this is our merge cost. This is the cost of 3. This is the cost of 2. From our, if we have only log n items, so k items, then we can merge in linear time. Or sorry, we can sort in linear time. So we just need to solve this recurrence. Well, how's it going to work? It's going to be kind of like merge sort, but not quite. So, question?
When you say, so you have, in step 2, you're merging 2 lists of sorted words into one sorted list of 2 sorted words. Does that imply actually taking the elements within the words and reshuffling them across words? Or you may have to do that, right?
Say that again?
So you have two sorted lists of R sorted words.
Yeah, the words are going to change. Which elements are in which words are changing. But that's thanks to step 1. For example, I mean, step 1 can merge any 2 sorted words and make one sorted word. Or actually, yeah, one sorted word. In our case, we're going to get 2 sorted words. That was the picture over here. I merged the 2 guys. I could represent it as one word that's kind of double full, and then I can split that into 2 words. So we, again, need the split operation, but split is just you mask these guys out, and you get the high part. This is all 0. Then you shift it over to the left, and now you've got the high word over as a single word. Yeah. So they are shuffling within those 2 words, or within one word, essentially, via this procedure, which we haven't covered. So everything's going to mix around, but then there's the low items and the high items. And so all the items in here are less than all the items in here. Other questions? Cool. So I need to solve this recurrence. So let's draw another recursion tree. It's an easy way to solve recurrences. Root is n over k log k. Next level down, see, n got divided by 2. So it's going to be half n over k log k. Half n over k log k. So the n gets divided by 2. So if I add up everything on this level, I get n over k log k. And in general, as I go down, all levels are going to sum to the same value, n over k log k. So up here, we're going to have a cost of n over k log k times the number of levels. Now, this is where it's a little tricky. This is not log n levels like regular merge sort. We stop at level k. So it's going to be log of n over k. That's the number of levels we get to. Now, at the leaf level, finally, we have things of size order k, and we only pay order k. Great. And then how many leaves are there? there's n over k leaves. Okay, so that's an order n cost. This is order k. There's n over k, order n. What's this thing? Well, what's k? K was log n, log n. So this is n divided by log n, log n. This, therefore, is approximately log n. So that log n cancels with this one. This is approximately log n. So that cancels with this one. So this is order n. That's why we chose these values. So this n over k was not actually that significant. We could have called that n. What is important is that this recursion doesn't work when you get down to a single word. Can't do the same strategy. You need to use a different merger for single words. Because here we have to do bit tricks. For this merge strategy, we didn't have to do bit tricks because everything was bigger than a word. Okay, so that's the reason. The reason why we have these two levels is not to make the time fast. It's just to make the algorithm work. I mean, to define the algorithm, there's within a word merging and over many words merging. The hard part is this one, within a word merging. So that's our next goal. But if we could do that, we get linear time sorting for packed sorting when you can fit log n things in a word. Any questions about packed sorting? Good. So last thing is, how do we merge two sorted words into one sorted word? And this is where we're going to use bitonic sorting. See, it says right here, bitonic sort for merging sorted words. Here, we know what to do. Much easier in hindsight. So I'm going to take a little diversion and tell you about bitonic sorting briefly. Because it's in CLRS, I don't want to spend too much time on it. But it is something we need, so you need to know how it works. So first thing is the idea of a bitonic sequence. This is going to be a cyclic shift of a unimodal sequence. So a non-decreasing plus a non-increasing sequence. So I want non-decreasing and then non-increasing. So this is a bitonic sequence. I think you know what this means. Or it could be a cyclic shift thereof. So I could, for example, take this part here and shift it over to this side. So then I'd end up with this, this, and this. This is also a bitonic. Or I could shift this whole thing and put it over there. And so I end up with that. That's also bitonic. So it basically has one max, one min, if you're reading it cyclically. One local max, one local min. Except it's non-decreasing, so a little messier, but same thing. OK, let's go over here. So if you have a bitonic sequence, there's something called a bitonic sorting network, which you can think of as a parallel sorting algorithm to sort such a thing. So it's almost sorted, but not quite. And there's this way of sorting them. So I'm going to draw a picture to make it easier for me. A little harder. It's a little more annoying to write down the general algorithm. So what I want to do, suppose the number of elements is a power of 2. Here's what I'm going to do. First, I compare the first and the midway element, and then the next one with the next one, and then the next one with the next one, the next one with the next one. For each of these comparisons, I put those items in the correct order. So if I do that 3 versus 6, 3 is less than 6, so 3 stays here, 6 stays there. 5 is bigger than 4, though, so 4 comes over here, 5 goes over here. Next is 7 versus 2, so 2 comes over here, 7 comes over here. 9 versus 0, so 0's over here, 9's over there. Okay, that's an easy set of comparisons to do. The nice thing is you can do all those in parallel. Okay, just to check here, this was a monotone increasing subsequence and then a monotone decreasing. Okay, now we have increasing, then decreasing, and then we have decreasing, then increasing. But if you look at the left half or the right half, they are still bitonic, and that's an invariant. Bitonic will be preserved here. Also notice all the elements in the left are smaller than all the elements in the right. That's not true for an arbitrary sequence, but it will be true for a bitonic sequence. Essentially, the max is somewhere here, and so it's going to be spanned by some of these intervals, that max. And by spanning those intervals, and in particular comparing that guy with somebody on the right, the max will get over to the right, and then the rest of the increasing and decreasing subsequences will follow. It's a very hand-wavy argument. You can see CLRS for a way to prove that. Okay, just take it for granted now. Now we recurse on the two sides. So I compare 3 with 2, 4 with 0. I compare 6 with 7, and 5 with 9. So what do I get? 2 is less than 3. 0 is less than 4. Then I compare 6 with 7, so 6 is less than 7. 5 is less than 9. So now I've got 4 chunks. This one, this one, this one, and this one. I recurse on each of them. So 0 is less than 2. 3 is less than 4. 5 is less than 6. 7 is less than 9. And now I have all my items in sorted order. Magically. Okay, but if you believe that invariant, that the smallest n over 2 items get to the left and the larger n over 2 items get to the right, then by induction this will sort them. It's kind of like quicksort in that sense. Okay, the cool thing is I can do all these in parallel, all these in parallel, all these in parallel, so the total time is log k if I'm a parallel sorting algorithm or sorting network. And log k is exactly what I can afford. So the last thing to do is to implement an operation like this or like this. This is kind of the generic picture here in constant time on a word RAM. One other thing is I don't want to sort a bitonic sequence. That wasn't my goal. My goal was to merge 2 sorted sequences. Okay, so I have 2 sorted sequences. I want to merge them. How do I make that bitonic? I just flip, okay, like that. I take this sequence and I reverse it. If I take a sorted sequence and reverse it, then it looks like this. And so then the result is bitonic. Then I can use bitonic sorting to sort it. So this is the merge problem, and I've just reduced it to bitonic sorting. Cool. Except, how do I reverse a sequence in log k time on a word RAM? Cute trick. If I have a word and it has many items in it, that's our picture, that's our setup here, and I want to reverse it overall, what I'll do is cut it in half. Take all these guys, put them over here. Take all these guys, put them over here. So I've got the right side. Sorry, it's only 4 cells over here. I've got the left side over here. Then I recursively recursively reverse this sequence and recursively reverse this sequence. And then I have the reverse sequence. Right? This is a standard, or one way to reverse items is to do the big part and then recursively reverse. Then I will get, this is like, AB reverse is equal to B reverse A reverse. Just a fun fact. So we're implementing that. Now how do I do this? Well, this is the thing I've been talking about over here. You want to take the high part, you just mask that part out, shift it to the right. You want to take the low part, just mask that part out. And so I can take each of these parts individually, shift this one to the left, shift this one to the right, or them together, and I've reversed. So this takes constant time. This is recursion, but the total number of steps will be order log k, which is exactly what I can afford. Okay, so that's how I do the reverse part. So if I want to merge, now I have a bitonic sequence. Last thing to do is how do I do this bitonic comparison in constant time? So that's the next page. Here's a quick sketch. I'm going to try to draw the generic picture. So the generic picture is I have this thing which I call A, and this thing which I call B, and we basically want to compare corresponding items in A and B. Though in fact there's another A over here and another B over here. In general there are many A's, many B's, but they appear in this nice periodic pattern. And so I'm just going to look at one A-B pair, but it's going to simultaneously work for all of them with the same operations. So that's the dot, dot, dot here. There's another A and then another B and another A and another B. So what do? First thing I do is make 1 AA, 1 AA, 1 AA. In other words, I add in these 1 bits. Remember, we had zeros there hanging out. That's when we're going to use them. So I set them all to 1s in the A list. I take the B list, I just shift it over and leave them as zeros. Okay, time for bit tricks. All right, then I take this number, I subtract it from this number. What do I get? I get zeros or 1s for whether this bit got borrowed, which tells me whether little a is bigger than little b. Then I get some junk, and then I get 0, 1, junk, so on, 0, 1, junk. Sure. So 0 corresponds to A being smaller than B, and 1 corresponds to the reverse. Okay, whatever. Then I do my usual masking. Just the 0, 1 bits, then there's some zeros. Okay, here's a new trick which we haven't seen yet. I'm going to shift this to the right by 2, or in general by the size of those items. So now I have 0, 1 here, 0, 1 here, and 0, 1 here. Each of these bits might be different. So I take this, shift it to the right. Now I subtract. What this gives me, so I'm taking 1, 0, 0, 0, minus 1. What I get is 0, 1, 1, 1. Okay, in this case there's just 2 bits. Except it's not 1, 1. It's either 0, get it right, either 0, 0 or 1, 1. And then we have here 0, and then 0, 0 or 1, 1. Okay, and so on. So now these are masks. The zeros correspond to when the A's were smaller. The 1s correspond to when the B's are smaller. So if I take this ANDed with this, I get the large B's. If I take this ANDed with this, I get the small A's, or some of those combinations. Okay. The point is, I think here I get the small A's, and then if I take this thing and negate it, and then mask it with this, I get the small b's. And then I take this thing, I ran out of room. So we've got small a's, small b's. I take this thing, I shift it over, so I have small b's here. And then I OR these together, I get all the smalls. Okay, these are designed to never conflict, because I took the inversion here. So I get the smaller of the A's, smaller of the B's. So now I put the smaller things in the right order. I do this exactly the same procedure negated, and I get the larges. Okay, then I OR these together, and I get sorted. Well, not sorted. I get whatever bitonic sort would have done. Right? It's doing these pairwise comparisons by doing this shift, and it's putting things in the right order. Taking the small ones always end up on the left, the large ones always end up on the right. That's the definition of the operation we want to do. Or is it bitonic operated? And because we're just doing shifts and subtractions and all these things, it works even though there's not just one A-B pair, but there's a whole bunch of A-B pairs. They will all be shifted and computed and sorted together. And so, a little hard to visualize, but this will do one bitonic operation and a constant number of word RAM operations. And so you pop all these stacks. This gives us a merger. That gives us pack sorting. And with pack sorting, we get signature sorting. Easy, right? All right, that's probably one of the most complicated algorithms we'll see in this class. But from that, you get a priority queue that runs in constant time provided W is a little bigger than log squared n. Boom.